For our last lesson in this unit, we're going to be discussing linearization and differentials. So let's just jump in and find out what this is all about. So the gist of this lesson is that we want to be able to approximate complicated functions that are curvy with simple functions, which are usually straight lines. And we've already done a little bit of this, but we're just going to formalize that language. So I want to demonstrate to you what I mean here by running you through just a quick little example. You can see here I've got decimals pulled up, and I'm going to graph y equals x squared. Come on, baby. All right, here we go. Y equals x squared. And then I happen to know that the tangent line at the point 1, 1 is y equals 2x minus 1. And you'll notice that those two functions intersect at 1, 1 at that green dot there. And so you can see that y equals x squared is obviously curvy, and y equals 2x minus 1 is obviously a straight line. But what we see when we zoom in, let me see if I can zoom in here, there we go. What we see when we zoom in is if I zoom in far enough, I can't tell the difference between the line and the curve. And this idea that we can zoom in close to a particular x value and notice that the line behaves exactly like the curve is exactly what we're looking for here. Doing this is called a linearization. Essentially, we're using the tangent line to approximate the function. Now, this is only true for values that are really close to x equals 1, right? This, if I zoom in over here at x equals 2, those stinkers are far apart. So this approximation only holds for values that are close to a particular point of tangency. Okay, so that's the example. That's the idea, that when you zoom in on a particular x value, the point of tangency, the tangent line behaves like the function. So our job becomes writing the equation for the tangent line. And we've done a little bit of this already. We've written some equations for tangent and normals. Now we're just going to formalize that process. So just like we did before, we're going to start with the old point-slope form. And you should remember from algebra class that the point-slope form is y minus y1, and y1 is a known point, equals m, which is our slope, times x minus x1. And x1 is the x-coordinate of the known point. And what we're going to do is we're just going to add a few different variables or names for these variables and then solve this thing. And we'll call that the linearization. So the first thing that we're going to do, so that our notation matches our textbook, is I'm going to call y L of x. And instead of having the point x1, y1, I'm going to simplify that so that we only need one value. So in the point-slope form, we have x1, y1. We're going to turn that into a point A, which will be known, and then the y value is just f of a. So now we are just talking about the language of a particular number, an x value, and then the function value. That means that y1 right here is now f of a. And then as I continue along, speaking the language of calculus, the slope, remember, that's just the value of the derivative at the point. So if I take the derivative and plug in a, that's the slope. So that's f prime of a. And then instead of x1, remember, we changed that to a. And I'm going to keep my x value because I want this linearization to be a function of x. Keep in mind that these blue and red values, these are numbers. So f of a is just a y value number. F prime of a is just a slope number. And this a is the x-coordinate number of our point. If I solve this equation for L of x by adding f of a to the other side, I get what we are going to call a linearization. L of x equals f of a, because I've added that over to the other side, plus f prime of a times x minus a. And this is just the calculus version of the point-slope form. And when you fill this in, you end up with an equation for the tangent line. And we are going to call that equation a linearization because we're using it to approximate the function f. So this thing is our linearization. And you're going to need to memorize this bad boy. L of x equals f of a plus f prime of a times x minus a. Say it to yourself 6 or 7 or 100 times so that you remember this. When we talk about a linearization in class, I want you to remember f of a plus f prime of a times x minus a. This shouldn't be something that you need to look up in your notes. So this bad boy right here is the linearization. Okay. So just so you know, this definition is also given to us in our textbook. This is on page 241, and if you want to get more information or read a little more on this topic of linearization, you can go to page 241 and you'll see this. Notice that this approximation, f of x is approximately equal to L of x, is called the standard linear approximation of f at a. We need to be close to x equals a for this approximation to be useful. So let's do a quick example. Let's consider the function f of x equals the square root of 1 plus x. And let's focus on the function values near x equals 0. Let's get a linearization for this function. So when they tell you that x equals 0, what we're really saying is that this is the value of a. So a equals 0. And then to get f of a, you simply plug 0 into this function and you end up getting the square root of 1, which is 1. Now, we're also going to need the value of the derivative at 0. So for that, we got to go ahead and compute the derivative. And we've worked with the square root function quite a bit. I happen to know that the derivative of the square root of u is just u prime over 2 square root of u. The derivative here is just 1 for this u here, so I'm just going to put 1 over 2 square root of 1 plus x. And when I do f prime of 0, that's just going to be 1 over 2. So the slope for us is, 1/2. And now we're ready to write out that linearization. L of x equals f of a was 1 plus f prime of a, which is 1/2, times x minus 0, better known as 1 plus x over 2. So this is the linearization that we can use to approximate the function square root of 1 plus x as long as we're near 0. Here's what it looks like if you were to graph these two. So the blue function is the original square root of 1 plus x curve. The red line is my tangent line 1 plus x over 2. And notice, as long as we zoom in, my goodness, I keep hitting the wrong button here. As long as we zoom in near the point x equals 0, like if I went like this, the red line and the blue curve basically look the same. All right, so that's the idea behind this linearization, that we can use a line to approximate a curve. So a good question to ask at this point is, how close is this approximation? If we take a look at the function that we just talked about, our approximation is just 1 plus x over 2. And so for values close to 0, like 0.2 or 0.05 or 0.005, we get these approximate values. 1.1, 1.025, 1.00250. Now if we actually plugged in the square root of 1.2, the true value would be 1.95445. You can see that written here. our approximation is very close. We're off by less than 100th. If we get closer to 0, we're off by less than 1,000th. And if we're very close to 0, this approximation is off by less than 100,000th. So it's pretty close, right? And depending on your needs, the linearization may be exactly what you need. I don't even know if that was a great sentence or not, but my point is the linearization may be a good approximation for the function. Let's do one more example. Let's take a look at the function f of x equals cosine x. And we'll focus on the point x equals pi over 2. So pi over 2 is our a value. Now we're going to need to know the derivative, right? And we're also going to need to know the y value. Let's do the derivative here. The derivative of cosine of x is negative sine of x. And so we need to compute f of pi over 2. Hopefully you remember your unit circle values. F of pi over 2 is the cosine of pi over 2, which happens to be 0. And f prime of pi over 2 is the opposite of the sine, right? So f prime of pi over 2, sine of pi over 2 is 1, so this thing's going to be negative 1. That means our slope is negative 1. And so our linearization, L of x, will be f of a, which we said was 0, 0 plus negative 1 times x minus pi over 2. And if we clean this up a little bit, our linearization ends up being pi over 2 minus x when you distribute that negative 1. So our linearization is pi over 2 minus x, and we're saying that that line will approximate the cosine curve as long as we're near pi over 2. Let's take a look at the graph and see how close we were. Again, you can see that if we zoom in, if we zoom in very close to pi over 2, right? I hope this doesn't give you a headache when you watch the video. When you zoom in close to pi over 2, the linearization behaves exactly like the function. So that's good news. Let's go ahead and summarize what we've talked about so far. The linearization is an approximation of a function for values close to x equals a. As we saw in the table earlier, the approximation is close but not exact. The question now becomes, can we find out how close without dealing with the original function? And for that, I need to introduce you to a new concept. Differentials. Let me explain what I mean. Up until now, when we've used Leibniz notation to represent derivatives, we've considered the d over the dx to be one operation. So if you wanted to find the derivative of y with respect to x, you'd stick a y there. If you wanted to find the derivative of f, you'd stick an f there, right there. And regardless of what you were trying to find the derivative of, this d over dx indicated, hey, go figure out what the derivative is, right? And we did that for other variables when we were doing our related rates. Well, it turns out that we can consider these notations in a different way. So let me introduce you to something new that looks exactly like that. Instead of dy over dx, where the d and the dx are one operation, let's consider these two things different pieces. So dy over dx. It looks exactly like the other thing, although I changed the color. But now these pieces are different. Each of these is called a differential. They're small changes in the variable. And we can do math with these little differentials the same way we would any other variable in algebra. Okay? So the idea is this, that we have this new notation, dy over dx. We're going to consider those individual pieces, and because we've done that, we can solve for them. Now, the dy over dx still equals f prime of x. I wrote f of x there, but that wasn't true. So this dy over dx was the derivative, and so is this new dy over dx. The difference is that I can do operations with these little pieces. Specifically, I can solve for dy. So if you multiply both sides of this thing by dx, you can cancel that dx there, and you come up with a new equation, which is dy equals f prime of x times dx. And this new thing, this new dy, that's called the differential. And the way you find dy, which is one of the main questions that we'll be working on in our exercises, is you just take the derivative and then you multiply by this symbol dx. You stick a dx next to the derivative. You literally just write the derivative down and then multiply it by dx, the letters dx. And then eventually we'll be given values to plug in for dx and for the function so we can compute what the dy is. Okay, so just to be clear, this new thing called dy is just f prime of x times dx. I'm not particularly happy with this explanation, but I'm hoping I can clear it up on the next slide. So the official definition in our textbook, which comes on page 244, explains a little more clearly what we were just discussing. If we have a function y equals f of x, which is differentiable, meaning the derivative exists on the domain, then there's a differential dx, which is an independent variable, and the differential for dy is dy equals f prime of x dx. We're just telling you what this differential is and how to compute it. Let me see if I can clear it up with an example. So let's take the function y equals f of x, which is x cubed minus 3 square root of x. And let's compute the differential for this function. So to find the dy for this function, we just need to do the derivative of the function times dx. So what is the derivative of y? Well, we'll do the power rule to get 3x squared, and then the derivative for 3 square root of x is going to be minus 3 over 2 square root of x. So that's the derivative, and we're ready to write down the differential. dy equals 3x squared minus 3 over 2 square root of x times dx. That's it. It's the derivative times dx. Now notice I had to put these parentheses in because my derivative had multiple terms. So you do put the derivative down and then multiply by dx, but you still have to follow the order of operations. And we don't want to violate the distributive property here. So place your terms in parentheses if there are more than one. But this is it. If you're asked to find dy, this is what you do. Now I know what you're thinking. Wait, what is dy? Well, let me show you in the graph, because dy is really just the change in y values of the linearization instead of the change in y values of the actual function. Or put another way, dy is an approximation for the change in y over an interval. And you can see in this graphic here that this change in the linearization, the original y value was f of a right here, and the new y value on the linearization is up here. Let me put it out there. All right, so we had this y value to start with, and we had this y value to end with. This distance right here is dy. Okay, it's precisely dy. It's the change in the linearization values. The actual change in the y values, so if you start at this y value, which is f of a, and you follow the function up to a plus delta x, or plus dx, that actual change is called delta y. So delta y is the actual change, dy is the approximation of that change. And when you subtract the actual change, delta y, minus the dy, that's called the approximation error. And it's usually the absolute value of that calculation. So the difference between the actual change and the approximation change is called the approximation error. It's how far off we were in our approximation. On the graph, what I'm talking about is this distance right here. That's the difference between the function value change and the differential. Let's look at one more example and we'll wrap this video up and we'll get you onto some exercises. So in example 4, we're going to consider the function f of x equals x squared plus 2x. And we're interested in the point a equals 1, so x equals 1 with a differential of 0.1. And then what we want to do is compute the approximation error. And remember, from the last slide, we said that the approximation error is the absolute value of delta y minus dy. So I'm going to need to figure out what delta y is and what dy is. Okay, so for delta y, that's the actual change in y values. So I'm going to need to compute f of 1.1, because it's x plus dx, minus f of 1. And if I plug 1.1 into this function, I'm coming up with 3.41. And when I plug 1 into this function, I'm coming up with 3. And that means that my delta y is 0.41. Now let's go over here and compute dy. Remember, dy is just the derivative. And our derivative is going to be 2x plus 2 times the differential dx. And when I plug the numbers in, I get dy equals, I'm plugging in 1, so that's going to be 2 plus 2, which is 4, times our dx, which is 0.1. So dy here is 0.4. And that means that our approximation error is 0.41 minus 0.4, which is 0.01. Our approximation error was 0.01. So the difference between where the actual curve ends up and where our linearization ended up is only 1/100th. Okay, so we've learned how to do a linearization. Remember, that's L of x equals f of a plus f prime of a times x minus a. And we've also learned how to talk about the difference between the approximation and the actual function with differentials. In particular, for differentials, you figure out dy by doing f prime of x times dx. If you're giving concrete numbers like we were in this example, you can actually compute the approximation error. Okay, that's enough for this video. Good luck on your lesson, and if you need anything, you know where to find me. Take care.